Hi, this is the presentation of VLDB 2023 demo paper, Lingui Manga, a generic large language model-centric system for data curation. I am Zui Chen from Tsinghua University and MIT. This work is collaborated with Dr. Lei Cao and Professor Sam Madden. So first of all, what is data curation? Data curation is essentially data cleaning, but more than just data cleaning. For example, it contains data discovery, data integration, and data cleaning tasks. Besides traditional data curation, during empirical application, there will be many extra tasks like event extraction, name extraction, anomaly detection, etc. In a nutshell, everything you might encounter during data preprocessing. The core challenge we are addressing is that as data curation is a wide-ranging research area, it was not likely to build a generic data curation system. This is where large language models, LLMs, can help. The goal of Lingui Manga is to introduce LLMs to help with data curation. Why do we need LLMs? As we have witnessed in the past year, ChatGPT and GPT-4, they have common sense and logical inference ability, which could help make many traditional tasks easier. For example, entity resolution for companies. IBM and Big Blue refer to the same company, but it is hard to deduce that via traditional methods, and hard to learn via machine learning unless there is this specific labeled data in the training set. In this case, LLMs with common sense are very helpful. On the other hand, why don't we just use LLM as a universal solution? There are many issues for current LLM usages. For example, LLMs could not be easily tuned for specific tasks. LLM could be expensive and slow. LLMs require manual prompt engineering. So essentially, we propose to build a system that serves as a bridge between users, LLMs, and local data. Eventually, we want to produce a mainly local solution that utilizes LLMs more efficiently. The traditional workflow, as shown here, requires users to communicate with the programmers or services. It requires tedious processing of data and repeated testing to obtain a solution that is potentially not the most effective. As we have mentioned before, LLMs could be better in many cases. And no matter whether the solution is rule-based or learning-based, many annotations or rules are required. In comparison, current workflow of naively using LLMs could directly produce an LLM-based solution, but it requires skilled users, the prompt engineers, and the solution is definitely not very efficient, considering the high cost in using cloud-based LLM services. In our proposed Lingui Manga system, users only communicate with the system, which encapsulated everything including LLMs, including local services, including processing of data. And the system produces an optimized LLM-powered local solution that has both the effectiveness of LLMs and the efficiency of a local solution. Our solution is suitable for rapid data curation application development for both professional programmers as well as low-code or even no-code users. That's because the user could easily communicate with the system in natural language and simple GUI. Let's first take a quick look on the system demo. The left part is operators. User can add operators for a specific functionality, which we'll see later. The middle part is executable. It's a localized solution, which includes code generated by LLM, code generated by the system, and support code written by the user if they want to. The right part is the workspace, showing the execution result on a specific dataset. Consider this name extraction example. First, let's see how to preprocess the input data. Here, the user can create a load data operator from a preset. He or she only needs to fill in the task description, input parameters, and output parameters. Optionally, user may provide examples to help our system understand the task. Then the system will ask LLM to generate code for loading data. We can see the generated Python code in the middle. If we execute the code, we get the data successfully loaded in the right part. Now, let's do name extraction. We have built-in pipeline, grammar component extraction, which contains a list of operators. The user only needs to define input and output, essentially what attribute to be extracted from what data source. If we now compile it, we get a complex code structure, including both LLM-generated code and our system-generated code. Notice that the code actually contains LLM invokes inside. That is, the generated code would ask an LLM to produce the output if necessary. After execution, we get the names extracted. The entire process is very easy, requires almost no coding. But we pursue more than just ease of use. We address the efficiency and effectiveness of our generated solution. The essential idea of improving efficiency and effectiveness is localizing computations as much as possible. For example, LLM code generation. Instead of running an LLM through mass amount of local data, let a small generated code script to process the data is much more efficient. We added validator, which checks the correctness for the generated code or LLM responses, which improves the effectiveness. We also introduced simulator, a local small machine learning model to imitate the LLM's response and bypass the LLM after accumulating enough training data. We also have connector, linking LLMs to more efficient and effective local data processing tools. For example, the naive LLM usage inputs a query to an LLM and gets a response. We first introduce an auto-validator, which would examine the correctness of response based on logical evaluation or user-provided examples. If incorrect, the prompt to LLM is improved. Then we add caching mechanism, a very simple simulator, which stores the LLM responses that could directly bypass LLMs on new queries that are similar to the cached ones. Finally, we have a simulator which collects the cached data to local storage and train a local model to replace the LLM. In this process, user only needs to add natural language suggestions as we presented in the demo. Similar for code generation, the LLM-generated code is verified and improved by the auto-validator before execution. The connector introduces third-party tools to be used by the code. An LLM query is also available, as LLM is allowed to generate a function that invokes itself. We conducted the experiments on different data curation tasks. The first is entity resolution. We demonstrated the benefit of our system to a no-code user. Without writing any code, the user could build an entity resolution application through our system with performance comparable to supervised machine learning, but using much less training data. And our method remarkably outperforms previous naive LLM methods. For our second experiment, data imputation, here we assume the user is a professional programmer, an expert. So providing code and instruction to the validator, we ended up with a mostly localized solution, getting comparable performance to supervised machine learning while using only 1/6 of LLM cost. We also performed a case study on the ease of use of our system over a real-world scenario of name extraction. We obtained a private data from a company containing multilingual web content. A local user is able to adapt the built-in pipeline of name extraction by simply adding one language detection module, which is created by the LLM. In conclusion, we introduced LinguiManga, a user-friendly and versatile system that serves as a bridge between users, LLMs, data, and solutions. It is both efficient and effective. For future works, we are still currently working on extending its functionality and introducing more components. We are welcome to see more attention drawn to the research of applying advancements in LLMs to data problems. That's all. Thank you for listening.